So if the mode of communication is analog in nature, then the analog receiver will receive a signal with noise, signal to noise ratio, let us say, input, and then you will receive a signal to noise ratio at the output. And always the quality of reception is based on the output signal to noise ratio. So this noise and the signal attenuation here and the noise that we receive here at the input of the receiver will pass through the receiver structure, whatever may be the receiver AM, FM or whatever it is, it will deliver one signal to noise ratio at the output. So we are satisfied with the, let us say, it has to be greater than or equal to 40 dB. Okay? Very good quality reception requires the signal to noise ratio at the output of the receiver to be of the order of 40 dB. So in order to ensure that quality, we need to transmit that amount of power, and in order to ensure the quality on the noise that is present in the channel, we can handle the transmitting power in our hand. So that is the only parameter which we can play with the transmitter and achieve the required quality. Now, if there is a constraint of increasing the transmitting power at will, then what do we do? How do you handle this noise? How do you handle the effect of noise, and how do you handle the loss of the signal that is experienced? So that is why people resort to if you want to use analog communication, then you will only have that option of increasing the signal power. But if there is not, that is also not possible, then how do you handle the effect of noise? So that is one disadvantage of analog communication. Okay? And that is why people wanted to convert the message itself into digital form, and digital modulation is digital communication is used, and there what we experience is there also it is a signal to noise ratio only at the input, but at the output, if here it is signal to noise ratio, digital receiver, let us say digital, here again the signal to noise ratio, same kind of channel, but here we look at the peak error rate, which has to be less than or equal to 10 power minus 5. Okay? So, because I am addressing the teachers, so I am not, I'm not going into every detail of what the system is all about. So I am just bringing about the salient features in order to bring about the understand the concepts behind it. So here the original message was analog, which was modulated, transmitted, received. Here the original message was analog and converted to digital. Digital signal is transmitted, and digital receiver is taking place. And at the output, you will deliver digital information 1010. Afterwards, it will convert to analog and deliver. So here also the quality depends upon the amount of error that is being experienced. Error at the input, you have transmitted one waveform, and that waveform is added with the noise, is getting attenuated and is received. Along with that, noise is added. But at the output, it is bits, and therefore the quality of reception required is marked 10 power minus 5. Now, how are we handling this noise? So, suppose in order to get that quality, in presence of this noise, this attenuation, if noise is more, if attenuation is more, then how do we get this required quality? We don't have an option to increase the signal power. Then what to do? Whereas here, we have the only option to increase the signal power, which was not possible, therefore we can't better it. But here, if we can't increase the signal power, maintaining the same signal power at the transmitter, experience the same amount of noise in the channel, there is a method of reducing the effect at the output of the receiver if we use what is known as error control coding. So error control coding is one thing. So in digital communication, what is possible is you convert the message into digital form and then add certain parity bits and then transmit. At the receiver, you will get this erroneous data here and then decode it. You get the reduce the effect of the noise. That means reduce the number of errors that you experience. So digital communication allows you to use what is known as error control coding in order to reduce the effect of noise at the output of the receiver. Without increasing the transmitting power, you have been able to reduce the effect of noise and therefore the quality of reception is improved. So that is one great advantage of digital communication. But then what is at the cost of what have we achieved this? So we have saved, otherwise what we would have done, we need to increase the power. So we could not increase the power, we saved the power. But we introduced this error control coding scheme in order to reduce the effect of noise. But at what expense? At the expense of bandwidth. So here, how are we saying that we are spending bandwidth in error control coding? Suppose you had bits. You had bits, say 110, 10 is to be transmitted. Corresponding waveform, let us say this is the kind of waveform that is transmitted. Okay, suppose this is a binary waveform. And if you want to encode, corresponding to this in this 5 bits duration itself, okay, you will add, let us say 3 more bits as the parity bits. Whether you will add 3 more bits or 2 more bits or any number of bits depends upon the technology, these different type of coding schemes which are not going into detail at the moment. But what we do is we add some extra bits into the original data, and those extra bits, let us say this 11010 has been converted into, say 1101001, let us say three extra bits have been added. So these 5 bits have become 8 bits, let us say. So these 8 bits have to be transmitted through this in the 5-bit duration itself. That means what? Here this time was divided into 5 divisions. 1, 2, 3, sorry. So 1, 2, 3, 4, 5. Now what we do? Same thing we will do. Say this is now 1, another 1, 0, then 1, then 0, 1, 0, then 1. So this 1, 1, 0, 1, 0, 1, 0, 1. That is it. So this is how we would have transmitted. So originally you had these bits coming at a particular rate. So now these 5 bits have been converted into 8 bits by adding 3 more bits. And let us say if this bit rate was let us say 1 kilobits per second originally, RB. Now after error control coding, RBC let us say becomes 1 into 8 by 5. So 8 by 5 so many kilobits per second. 1.6 kilobits per second. So you look at here, these bits were coming at 1 kilobits per second, you had a waveform like this, and this waveform was modulated, transmitted and received this. And now what we are doing, adding 3 more bits here in order to facilitate error control coding, and the bit rate effectively becomes 1.6 kilobits per second. That means in the same duration you are transmitting 8 bits. So effectively the pulse width has come down. For one you had so much of duration, now for one the duration has been reduced according to this. So 5 by 8 times it is reduced. So pulse width has come down. Earlier the 1 was represented with this kind of a width, the 1. Now the 1 is represented with only this width. This is 1. So what happened? This one is again modulated, transmitted and received, and ultimately it will help you detect and correct the error. So we made one statement saying that we are able to achieve, reduce the effect of noise by not increasing the transmitted power but spending extra bandwidth. How am I saying that I have spent extra bandwidth? That is, my data rate has increased because of the additional bits that I have added, and now this requires extra bandwidth. So for which now we have to understand bandwidth requirement of a particular waveform. So I just maybe I will be knowing, but I will recall the spectrum of these waveforms. So corresponding to this particular waveform and this particular waveform, let us say this is TB, and this is TC, let us say. So corresponding to this, each one of these pulses, if you see the spectrum, okay, you have a sin x by x spectrum, power spectrum. I like the power spectrum. So it is something like this. It goes. So corresponding to this is 1 by TB. This is minus 1 by TB. For this, if you draw the spectrum, you find this is 1 by TC. 1 by TC. So the pulse width has come down. So 1 by TC is larger than 1 by TB. Ideally speaking, you require infinite bandwidth for transmitting such pulses. And if you modulate this onto a carrier, then also it will result in the same kind of a spectrum around the carrier frequency. So, what is the practical bandwidth that is required for transmitting? People have accepted the main lobe bandwidth. Let us say the main lobe itself contains the maximum energy of all this. So, maybe 95%, more than 95% of the energy is in the main lobe. Therefore, it is enough if you transmit this pulse through a bandwidth of say 1 by TB, okay? But this pulse, because of that suppression of the other lobes, the pulse that is received will be only like this, small distortion will take place, which is acceptable, which can be handled later on. We will see later on the technology. So bandwidth required is only 0 to TB, whereas for this the bandwidth required is this much, 0 to 1 by t. This is the bandwidth required. So bandwidth required is, in this case, is higher than that of the previous case. That means this is the case where we have added parity bits, which resulted in reduced pulse width for the bits, and which resulted in higher bandwidth requirement in the channel, and has been transmitted and received, and achieving reducing the effect of noise here. That means previously the bit rate was 10 power minus 3, for example. It can be brought down to 10 power minus 5 by introducing such such error control coding schemes. That is a subject by itself. A lot of schemes are available. We don't have to worry about it at the moment. But such a powerful scheme or powerful technique has been used in order to handle the effect of noise. Okay, so we are now seeing there is an interplay, exchange between the power and the bandwidth. So this trade-off, if you want to save power, you have to necessarily spend bandwidth in order to achieve the same quality of reception. So if you want to save power, you spend the bandwidth. Similarly, vice versa also will be true. If you want to save the bandwidth, you need to spend a little more power. We will come to later such instances we will show. So, coming back to our discussion, wireless channel was introducing noise attenuation, okay, and traditionally it was analog, now it has become digital because it has got one such advantage. This is one advantage of digital communication. Like this, there are many other advantages for providing security of the data. In analog communication, you will not be able to provide security, whereas in digital, you can resort to encryption, decryption methods and convert. There you don't have to spend extra bandwidth. Okay, you only jumble the bits in a certain manner so that it will offer certain kind of security and which can be achieved. And that is easily done in digital communication. So that is a big advantage. One is error control coding, another is security that it can provide. So, and similarly, in long distance transmission also, digital communication method offers what is known as regenerative repeaters. Okay, as I told you, we want to cover a long distance, one repeater to another repeater to another repeater like this. When the signal is relayed. Now, the job of the repeater is to receive the signal, demodulate, and then remodulate, transmit it. Again, it reaches another repeater, demodulate, remodulate, transmit. So, in analog system, when it demodulates and remodulates, the noise could not be removed at the repeater. Noise also gets carried to the demodulates and then amplify and remodulate actually at the repeater. There is an amplifier, so noise also gets amplified there. Whereas in digital communication, when you demodulate, so you know what is the pulse shape of the signal is known to the receiver as a repeater in digital communication. Whereas in analog communication, the shape of the signal is not known to the receiver. Shape is, suppose speech waveform is like this. This is not known to the repeater, so that it will amplify only the speech waveform. When it receives speech plus noise, both will get amplified at the analog repeater. Whereas in digital, there also it will get noisy waveform is amplified in analog. Here also the noisy waveform is received, but it can regenerate original pulse at the repeater itself, then remodulates it. Because it knows the shape of the signal. For a 1, we have represented it as a pulse. For a 0, a negative pulse. So the repeater knows that 1 is transmitted using one positive pulse, 0 is transmitted using negative pulse. Or 1 is positive and 0 is 0. That knowledge is there. What it does not know is, in a given point of time, whether it was 0 or a 1 that was transmitted, it does not know. That is what is to be done. So, the repeaters in the digital communication are called regenerative repeaters because the data waveform is regenerated at the repeater itself and then remodulated, transmitted. Whereas in analog repeaters, the original waveform cannot be obtained. Along with the noise only, it gets amplified and transmitted. So there is a disadvantage. So analog digital communication enables you to have what is known as regenerative repeaters. These are the three main advantages of digital communication: error control coding, encryption, decryption, and regenerative repeaters. And it has got many other. As a consequence of digital communication, the other technologies, modulation has to be digital modulation, multiplexes has to be digital, multiplexing has to be digital, so they will follow. So that is how one meets the requirement of mitigates the effects of the channel. These two are the experience even in wired channel. Wired channel also introduces noise. Wired channel also experiences attenuation. And there, if you are using analog communication, this is what is going to happen. With digital communication, you get these kind of advantages. These are all true in wired communication also. And spending extra bandwidth in wired communication is not a matter, because coaxial cable, higher bandwidth cables are available, fiber optic cables are available. So spending bandwidth is not an issue at all. Okay, so if you want more and more services to be given, you can have to lay more and more cables. Only thing is the physical infrastructure has to be laid, and which may be a costly proposition, which may be cumbersome in certain cases. Now, having identified the requirement of a wireless channel for wireless communication, as I was pointing out, to the mobile communication. Mobile now, as we all experience these days, anytime, anywhere, anybody communication is required. You require what is known as the pervasive connectivity. So, for which wireless medium is the only medium you can use, and that too on the terrain when you experience multipath reception. Now, what happens to the signal when you this introduces distortion. Okay, so here the noise was getting added, there was an attenuation and then distortion. The waveform will be distorted. You will transmit a pulse like this, but if there is a multipath transmission, you may receive it in a different distorted pulse like this. So it will give you introduce what is known as distortion. Distortion also happens in wired channel because of the limited bandwidth that one offers, and therefore distortion is a different kind of a complex distortion that we experience. So multipath reception will give you distorted signal. So if this is happening, then what is the technology you can select in order to mitigate this kind of effects? So ultimately, it is leading to understanding the wireless channel, behavior of the wireless channel, and what are all the technologies or techniques that we employ in order to mitigate the effects of wireless channel like distortion, attenuation, and noise. And at the same time, you want to offer this channel to more and more people. Same resource now in this case, what are the another important issue that we have to understand now is the communication resources. Along with this, one more issue is also to point out. As I told you, signal power is one parameter, resource. Bandwidth is another resource. And if you want to achieve this, as I told you, you will spend bandwidth in order to save power. For which you use one technique, error control coding technique, which has increased the complexity of the system. System complexity has increased. As you go on exchanging your resources, one resource with another resource, you need a complex technology, complex system, complex algorithms, in order to reduce the effect of all these things. So error control coding is one such thing which has been used to reduce the effect of the noise. And as a result, there is one level of system complexity, increase in system complexity. Similarly, there is distortion here. Now, if you want to reduce the distortion effect, you need equalization. So, equalizers are a little more complex, and they introduce increased system complexity, and there will be associated processing delay taking place. So, all these have to be accounted. So this is one type. Now let us stop.